Okay, in this example, we're going to run through writing the node equations for the three nodes in this circuit. Okay, so there's three unknown nodes, VA, VB, VC. I have them marked here. In general, you don't get those shown to you if you're analyzing a circuit. There's the circuit, you have to identify the nodes. But here they are. Let's go ahead and write node equations at each of the nodes. So remember, node equations are KCL. All right. So the idea here is we need to find the currents. All right. So let's take node A, and let me use a blue marker for the currents. All right. So I have this current coming up, this current coming across, and this current coming down. I reference them all coming out of the node. All right. So let's take the first one. The current coming up vertically through the 8 ohm resistor. So we notice here that this branch has a couple of resistors in it, all right, and a voltage source. All right, so mentally I replace this with an equivalent resistance. Okay, so 8 plus 6 is 14, and then the 10 volts. Okay, and then this would be VC and VA. All right. So if I have that, I can then move the dot to the other side of the equivalent resistance. All right. So let me change the dot to red. Okay. So if this is VC, all right, here's VC. This is 10 volts at this source. If I slide this dot over, this is plus. That looks like a current source. Sorry, let me redraw that. This is plus minus 10 volts, the same one that's here. All right, so if this is VC, on the other side of this, from plus to minus, I would have a drop. It's like an elevation drop like we talked about before. So this would be VC minus 10. All right, and then the other side here is VA. So I now have the voltage on either side of this 14 ohm equivalent resistance. All right, and so if I reference that coming up like I have done here, that first current going up would be, okay, you do, VA first because the current's going up, minus the other side of the dot. This other side of the dot is VC minus 10, minus parentheses VC minus 10. Okay, divide by the equivalent resistance. The equivalent resistance is 14. Boom, we've done that current. All right, so let's now do this one. This one's really easy because it's an independent current source moving in the opposite direction of what I have referenced. So this would be a minus 3. And then the current coming down, I look at the whole branch and I see, here's VA. I can slide this dot down. Here's VA. All right, but I have an equivalent resistance here of 9 ohms, and this would be 0 volts. So what I would have next is VA minus 0 over the equivalent resistance, which is 9, equals 0. Okay, so there's the first node equation at node VA. All right, so let's now take a look at node VB. Let's change the marker color to purple in this case. So what I want is all the currents coming out. I reference everything coming out. And then I take them one at a time. So starting here, this one's easy. That's 3 amps. Okay, it's an independent current source, matches the direction, so it's positive 3 amps. Okay, if this is VB right here, here's VB, what is the other side of it? I start at VB, I have a drop of 12, so this would be VB minus 12. Okay, so I now have the resistor. Have dots on either side of a resistor, so I can find that current coming down. All right, so that would be VB. It's going down, so it's the top dot minus the bottom dot. VB minus 12 minus 0 divided by 15. Okay, so that's the current coming down at node VB. Now the current coming across at node VB, that's right here. Okay, so I see here's VB on one side of the resistor, VC is on the other, so it would be VB minus VC. The B's first because I'm in this direction. All right, divide by 9 equals 0. Okay, so there's the node equation at VB. All right, so you can see these are very systematic things to do. All right, let's change this to green and do VC. All right, so for VC, I have currents coming out of the node. All right, so let's do this first one coming to the left. That would be VC minus VB divided by the equivalent resistance of that branch, which is 9. Okay, moving up. All right, moving up, this upper branch has this equivalent circuit. Okay, so it's the same idea. Here's VC. Here's VC. We move this over. Here's VC minus 10, plus minus 10, and we get to the 14 volt drop. But we want things going this direction this time. So it would be VC minus 10 minus VA divided by 14. Okay, so that's this current coming this way. I mentally drew an equivalent resistance for that branch. Okay, I actually physically drew it right here. All right, so hopefully you see that. Those are the trickier ones. All right, and then finally we have this current coming down, and there's only a single resistor, so this would be plus VC over 20 equals 0. All right, those are the node equations. We can solve these, and I'm going to go ahead into MATLAB and solve this and paste this into the solution so that you can take a look at it, and that way you'll know exactly how to solve these things. Okay, so at this point I've put all of these equations into MATLAB, and we've talked about this before, where we enter the equations. This is node A equation, this is node B equation, this is the node C equation, and we just put this into the symbolic solve for the variables VA, VB, and VC. Okay, so the other thing I wanted to point out is at this point it'd be nice if we had a way to double checking our work. And one of the things we can do is we can calculate the power associated with each element, and then we know from principles of conservation of power and energy that the power supplied should be equal to the power used. Okay, and so that's what I did here. I calculated the power for each of the active elements. For all of these, I use the active sign convention. Okay, so let's talk about how that would work. So look at the 10 volt source. All right, if I want to use the active sign convention for the 10 volt source, I need to know the current moving in this direction. Okay, so maybe I'd call that I10. All right, so from our picture here, we know that I10 can be found from the node voltages. All right, so we already have our equivalent circuit. If we want the current being referenced to the left, this would be VA minus VC minus 10 divided by the equivalent resistance 14. So this comes from this little equivalent circuit that we can mentally do, or we can write that down and get it. That would be the current using the active sign convention going through the 10 volt source. Okay, so once you know that, you can plug that in here. All right, so that's what I have here, the current for the 10 volt source multiplied by 10. That gives me that power for that active source. Okay, same thing with the 3 amp source, right? If I want to know the power associated with the 3 amp source, I need to know the voltage across it times the current through it. Well, the current's 3 amps because it's a current source. So the voltage across it would be VA minus VB, with VA being plus because it's the active sign convention. Okay, so that's what I have there for the power for the 3 amp source. Okay, same thing with the 12 volt source. I use the active sign convention. That's why I have 0 minus VB minus 12 over 15. So going back to look at the circuit, I want the current coming this way. All right, so 0 minus VB over 12 divided by 15 would give me the current coming up through, so it would be coming out of the plus terminal of the voltage source. That's the active sign convention. Okay, so from there, that would give me, have the current here times the voltage 12. That gives me the power for the active source. Well, the resistor values are usually pretty easy to get once you have the node voltages. So I calculated the used power. And in fact, you don't really need to worry about which direction the current flows or which way the voltage is for a resistor, because the formula is always going to be I squared times R or V squared over R. And this squaring means you don't need to really worry about the polarity. And we know that because resistors always use power. All right, so these are the calculations for all the resistors. Of course, these are passive, and so we knew to use the passive sign convention, but that's pretty straightforward. That's how we normally do it. Okay, so from there, the way I can check my work is I add up all the power supplied using the active sign convention and compare that to the power used. And we see here that these match up, which makes us feel pretty good about our answers. Okay, so that's how you do that, and hopefully this example helps you learn how we apply node voltage techniques to analyze circuits that are reasonably complex, right? This was a 3-loop circuit with lots of elements connected, and we can systematically write the equations and solve them to analyze this circuit.